Ma'am, Uma Maheshwari, ma'am.
Yes, sir.
Yes, ma'am. Ma'am, shall we start, ma'am?
Yes, sir.
Okay, ma'am. Thank you, ma'am. Okay, dear participants, very good afternoon. Today, day 4, second session. AICT sponsored 2 weeks online faculty development program on emerging trends and challenges in VLSI mixed signal processing for fourth industrial revolution. Today topic PCB design demo in EDA tools. Today our resource person Mrs. Uma Maheshwari, Manager Technology, Paramra Software Private Limited, Coimbatore, Tamil Nadu. So welcoming, ma'am.
Thank you, sir. Thank you for your welcome.
Yes,
And
ma'am.
very good afternoon to all present here.
Yes, ma'am. Thank you, ma'am. Ma'am, before going to session, small introduction about our today resource person, introduced by our student, Mr. Rakesh, to introduce our resource person.
When life puts think training in this way, I'd like to introduce our today's resource person, Mrs. Uma Maheshwari, Manager Technology from Paramra Software Private Limited, Coimbatore, of more than 20 years. She is pursuing part-time PhD in the area of EMI filter design. She had completed ME in Embedded Systems and Technologies in Anna University. She had completed B Institute of Technology, Coimbatore. Her area of expertise include high-speed PCB design, post-processing of PCB design, process improvement, 10 technical articles in referred national and international journals. She had published the books in the title of Power Electronics with MATLAB, Simulating Tools for Electrical Systems, writing book in the title Electrical Machines with MATLAB. She had conducted one credit course system and EMI mitigation methods. She had certified Japanese language proficiency tests. She acted as a keynote speaker in various international and national workshops. Now I request our today's resource person, Mrs. Uma Maheshwari, to deliver her speech on the topic of PCB design demo in EDA tools. Please, ma'am.
Thank you, Rakesh, for your kind introduction. And I would like to wish all of you a very good afternoon who are present here. So after lunchtime, I think it will be good to have a demo kind of session rather complete theory oriented. So let me share my screen first. Hope I am audible.
Yes, ma'am, you are audible, ma'am.
Thank you. Thank you. Okay, so my topic of presentation and my experience is also in the side of PCB design area domain. So for any electrical or electronics engineer or communication engineer, if you take it is not is a part of curriculum. Like students will not study about the PCB circuit design and concepts related to that. This may be a little eye opener for any electrical or electronics engineers. So for if you take any products, electronics products or electronic circuits, if you any somebody is asking, what should I do, sir? Karthik, sir. Hello.
Ma'am, you are audible, ma'am.
Yeah, some messages coming, sir. What should I do?
What messages, ma'am?
Can you able to see my screen, sir?
Ah, yes, ma'am. We are able to see.
Sima is requesting remote control of your screen. Can I decline, sir?
Yes, ma'am.
Okay. So if you take any product, even right from a mobile phone to laptop or any IoT related products, you will be having definitely a PCB circuit inside that product. So you might have done many research or many other circuit design, if it is a high complex or the high complexity design, you definitely need a printed circuit board for the circuit to work. You cannot use breadboard or some other thing for complex designs. So again, the G. Narasimha sir is asking the remote control of my session. Okay. So the printed circuit board design is very common for electrical and electronics engineers. So let us see about how to design a simple PCB, and from that you can build on your own PCB or complex designs or whatever it may, research projects or whatever it may be. So let me first give you a brief introduction about the PCB and how the design flows. So small 2 presentations are there from my side to explain about the PCB and the components, what are all the parameters involved in the PCB, and how the design flow happens in an EDA tool. So let us start the first presentation. It is just giving the brief introduction about the PCBs. So we'll see what is PCB and what are the parts of the PCB and what is the unit we should use for designing the PCB, and some of the PCB design considerations, and what are the standards we should use while designing PCB. And so what is PCB? As we know, PCB is printed circuit board. So circuit is printed on a non-conductive material, like based on your circuit withstanding temperature capacity or temperature handling type. We should use the board material such that it can work within the specified parameters. So printed circuit board is a board where the fiberglass or the composite epoxy can be used as a base material upon which the copper can be traced out or wired out or etched out according to your circuit connections. So it is actually it is printed on a board. So that is why it is called a printed circuit board. So commonly used board material is FR4. It is a glass epoxy which is commonly used for the board material. And some of the components used in the PCB, that is parts of the PCBs, are components, pads, traces, vias, and layers. So these are the main parameters, that is main terms which are the parts of the PCB. So coming to the component we all know it may be the single sided PCB or double-sided PCB or multi-layer PCB. There will be a component sitting on it. So the components can be of 2 categories, like leaded components or leadless components. So there are many huge advantages over the leaded components to the SMD components, that is leadless components. So lead inductance is minimized in case of high, if you are using to the high speed design. So lead inductance will be the main criteria for the signal integrity issues. So what we do is, instead of lead components, we'll use the leadless components. And one more advantage is floor utilization, that is PCB area utilization is very, very minimal in case of leadless component. So conventional circuits normally use the leaded components. So that is the picture shown here. That is some of the resistor or maybe capacitor which has the 2 leads. In some cases the ICs will be having the lead which can be drilled soldered on the PCB using the drill. So another type of PCB is leadless component we discussed, right? So leadless component will not have the drill on the board side. So it just sits on the board, either top side or the bottom side, and we can paste the surface of the component to the board using some glue or some materials, like it is like a soldering thing. Because of this various advantages of the surface mount components or leadless components, we are using the thing very commonly. So these are some of the DIP components. That is, there are multiple packages are available for the component side. So dual inline package, plastic leader chip carrier, so SOIC package, so BGA, ball grid array, and FPGA. So various types of packages are available for the component side. That may be a so we discussed lead and leadless components. So under the leadless components, there is another category called array, wall grid array components. Like the surface of the component will have the balls which will be sitting, which is going to be sit in the on the PCB side. So that there will be a reflow process for the attaching the board to the ball grid array. It can be FPGA or LPGA or whatever it may be. So there are various types of vias available in case of the PCB. So there are, if you want to solder a component from from the top to bottom side. So this is actually we consider as a top side. This can be a bottom side. So here, so from the top to bottom side, so there is a drill present over here. And after drilling the PCB, there are the walls of the PCB can be plated through the via the copper material, so that the complete connectivity can happen for the component. So another types of vias are blind vias and buried via. So these vias are used to utilize the space of the PCB. So even though the manufacturing cost of this blind and buried vias are costly, in case of high efficient and less space board, less dimensional board, we use this particular technology for connecting the one layer to another layer. So because of this wall plated, we are getting the connectivity between the layers. So that is the important point to be noted here. So another part of the PCBs are pads. So pads are nothing but the copper pattern which is sitting on the PCB. So it can be a round shape, or it can be a rectangular shape, or it can be a square shape, where the component or the traces can be, traces means the connection between the two components can be established using this pad location. So these pads are nothing but you can, it's a copper pattern, copper shapes, you can say, where you can connect all the components. So now, third one is the traces. Traces means it is considered as a external wires. In the case of PCB, you can call it as a traces. So it can also be called as a tracks. So in some geography, that is in some countries, they will call as a tracks or traces. And it is we can consider it is equivalent to a wire for conducting the signals. So it can be a power trace, or it can be a signal trace. So based on the trace current carrying capacity or other power carrying capacity, we will define the trace width. So so the traces are made up of the copper material. So this process of tracing, that is this process of wiring, is called routing. So the routing is another term which is to be noted here. And routing means, as we discussed, is a process of making the connections as per the circuit diagram. So that if it is sometimes there may be a dense board, then circuit connections will be establishing between the component or between the pads. So what we'll do is we'll neck down some of the portions alone, and as shown in the figure, we'll to maintain the distance between this copper and the pad copper, that is trace copper and the pad copper, we'll reduce the line width, and we'll make that line, and it is called as a neck down, and we'll extend an as per the previous trace segment, we'll continue. So because of this gap restriction, we'll make the neck down traces. So that is also possible in the case of routing. So before doing the routing, what we'll do is we'll all place the components initially, and we'll make the connections between the components using the connections like the rubber band line, that is called rat's nest. So these rubber band lines are considered as a connectivity between the pins. Like this, for example, if you take this red color line from this pin to this pin, IC, it is getting connected, and from here to this another component is getting connected. So this will be the reference point for making the connections. So this will be established from the circuit diagram. So while routing the traces, we need to follow certain rules. It should have a smooth flow of signal. Like you should not have the acute angle between the traces, between the line segments. So right side shows the bad routing and left side shows the good routing, good pattern of routing. So similarly, so you should not use this 90-degree angle. So it has to be 135-degree, or from this side it is a 45-degree. So you have to have the clear and smooth signal for good signal integrity. So here I have shown some of the segments, like segments which are all the technical terminologies which is used in the EDA tools. Like this is the trace and pads, both are the copper pattern actually. So we need to maintain definitely a certain distance for the cross, to avoid the crosstalk or the short signal to pad short, or for whatever the issue it may be. So we need to maintain some of the small distance between the copper signals, copper patterns. So for if it is a trace and the pad distance, means it is called as track to pad, and if this is actually a pad, so this we call it as land size, and this is actually a drill size, it is hole size. This distance between the pad to pad is called pad to pad distance, and width of the trace is called as a trace width. And of course, the between the signals, that is between the traces also, we need to maintain some of the distance. And if it is a NPTH is a non-plated through hole, this hole is drilled for mounting purpose, and this also has to be away from the copper pattern. So if it is drilled or touched in the copper pattern, the mounting for pad to trace violation can happen. So next is vias. So in the previous slides, we saw different types of vias. So this is also the same continuation with that. So this is also same as the pads, like it is a copper pattern, which is only used for connecting between the layers of the PCB. So you'll see the layer concepts in later slides. So this is, we need to minimize the vias count actually. So if vias is nothing but we say, as we discussed, vias are nothing but the pads which has a drill inside the PCB, and the drill, if you drill more in the PCB, you will definitely have the inductance effect in the high frequency applications. So minimizing the vias are best solution for reducing the inductance level in the frequency. So low frequency board doesn't have the impact on the vias locations or the vias count. So this is a cross-section diagram shows on the, either it can be a capture pad or a via pad. So if you drill the via, after drilling the via, the walls of the boards are plated using the copper. So that is the major advantage of the connection between the one layer to the another layer. So we'll see what is layers. So layers are the thin sheets of material. So that is the copper material only. Between the copper material, we will have the dielectric, that is board material, like FR4 or polymer, whatever it may be, depending upon your application or circuit operation. And there are, if it is a simple circuit, we will use single layer PCB. If it is a little complex, we can go for 2-layer PCB, that is top layer and bottom layer. In case if your circuit is very complex, like motherboard circuit or the defense related things, so where you definitely use for multi-layer circuit. Also in the multi-layer, you will have definitely a size reduction instead of having the bigger size. So there in the multi-layer board we'll have definitely a top layer, that is top metal layer, and the second definitely the bottom layer will be there, and in between the we'll be having the internal layer. So top layer, in bottom layer, and internal layers, or the stack up of the PCB. So internal layer will be having signal layer and power layer, or the ground layer. Definitely the ground will be there, and power can be you can use you can connect the power as a traces or the complete copper pattern, that is copper core of a layer. So signal definitely should be a traces, and which can be routed from the from the reference like rubber band lines or from the circuit. So so these consist of the internal layers, above which, that is above the top layer, you will have definitely a mask layer, which you see as a green color. Normally it is a green LPI mask. Some cases it will be the brown, or some cases it will be a pale yellow. So there will be a different types of mask. So that also depending upon your applications or heat withstanding capacity of the PCB or the environment. So you can select the mask layer, which is only for the protection purpose, which will protect the top layer from the external influences. So the copper definitely reacts with air, there is moisture content in the air. So coating the mask layer on the top of the copper layer, copper traces will prevent the erosion. And above the top mask layer, we will have the silk layer. The silk layer will be the text layer. That is, if you are using the one BGA or the capacitor or the power supply, whatever it may be, you will have to have definitely indicate it is a BGA or it is a power module, or it is a whatever it may be. You have to designate that component. For that purpose, the silk layer is used. It is just text layer, which you see in the PCB on the top side or the bottom side. And similarly, the bottom layer have the bottom mask layer and the bottom silk layer. So here you can see the green color, which is a mask layer, which is coated on the top portion of the PCB. For example, here there is mask opening is happening. So why it is happening? Mask is a non-conductive material, and if you pour the mask, that is, if you coat the mask on the top of this kind of copper, you cannot solder the PCB. Means that solder lead will not sit on the mask, and that component cannot be installed. So for that purpose, component accessible locations will not be covered with the mask. Other locations will be covered with the mask. And the text you see in the white color is actually called a silk layer. So for example, here the RST, the 3 volt, 5 volt ground, and so the text will be helped during the process of assembly, or in the case of repair or rework and whatever the criteria it may be. But the assembler will not know what is going to be installed here. So the text layer is very important, and they should be legible and readable. Otherwise, assembly will not happen. So similarly, we talked about the mask layer. Mask layer is only for protection purpose. So board material. So we'll be having the board material initially as a base material. So you can choose the various board material based on your application. So there will be 3 types of terminologies will be used. One is core, the second is a prepeg, and copper foil. We'll see. So here the core initially, if it is a 2-layer board, we'll take this alone, because where here the center portion is the top non-conductive material like board material. It is called as a board material, upon which the copper is coated. So both the sides are coated. So that is called a core as a set, as a whole. There is 2 sides copper and one with one dielectric is called a core. And upon which one prepeg layer, this is also non-conductive material, which is inserted between the core and other copper sheet, copper clad it is called. So this prepeg will be cured to sit on this core. So the complete setup is shown here. So you can see the core is center portion is the core. In case of two-layer PCB, we will take only one core. And in case of multi-layer PCB, we will use prepaid, and after that the copper foil will be used. So the pre-peg and the core material or the non-conductive material. Only the copper will be conducted, and based on your circuit and based on your design, the remaining coppers will be etched out, and the acidic copper will be remained. So the same concept I have explained earlier is shown here. So there are two coppers. So it is if it is a multi-layer board, definitely we may use the two cores or two or more cores inside the PCB. So this is a typical cross section of the multi-layer design, where you can see two cores are present here. Here one core and second core, and upon which the pre-peg and the copper foil is coated here. So this is a 8-layer PCB. How they'll stacked up the 8-layer PCB. So in center portion, definitely, as I said, the core will have the ground and the power. In the case of this example, so this may be a copper foil, and upon which the copper foil, another non-conductive material, and another core with the conductive material both sides, and pre-peg and the conductor. So alternate layers will be the copper materials, and the alternate layers will be the dielectric materials. Routing the traces from here to this pad, okay, then from here to this pad, and another signal is coming from this pin to this pin, and we need to connect this pin to this pin actually. So if this wire that is this traces is crossing here, we cannot use this top layer to connect the plane. So for that, what we are using this next layer and connect the same pin. So that these two signals will not get shorted. So this is the concept of via routing. So normally we use two types of units, that is English units, metric units. So in US and Europe will have the English units, and Asian countries will normally follow the metric units. So there are correlations between those units. That is 1 inch is equal to 25.4 mm. So based on your unit design, what you choose is you can use those calculations. And coming to the standards, so for whatever you do, you'll have to benchmark with the standards. So like similarly, for the PCB design, you have the IPC standards. So IPC is interconnecting and packaging circuits, electronic circuits. So this organization defines the standard for each and every activity or every terminologies we use inside the PCB. So some of the most of the PCBs will be following by this IPC standards. So some research and R&D experiments will not follow this IPC. So that is not a issue. But if you are selling a product or in the market, definitely it should follow the standards. And there are three types of classes in the PCB design area. So one is based on the general electronic product, you'll have some tolerances. And if it is a dedicated service electronic product, you will have some other definitions like instruments, military equipment, where some of the cosmetic imperfections are allowed. So the tolerance will be the medium range, moderate range. And class 3 is a highly reliable electronic products, like where you need a continuous performance is measured. It can be measured, and it is a very critical. Like you can say it's a military products or medical products. You will have to have a tight tolerance of the standard. So the standards will have the, for any product, if you take the standards, there will be a 3 types of classes: class 1, class 2, class 3. Depending upon your circuit or application, you will choose the standard like class 1 or class 2 or class 3. So as we discussed, there are many, there are types of boards based on the layers you can define, like single-sided board, double-sided board, that is 2-layer board, multi-layer board, with drill, without drill, with core, without core. So like, so this is the one type of thing. And another type, based on the technology, you have the rigid PCBs, what you see in the mobile phone or IoT projects. So another thing is the flexible PCBs. Another is the rigid flex PCB, the combination of rigid and flex PCBs. So just have a look at the rigid PCB. So the name itself indicates the board material is very rigid, cannot be bent. So next is a flexible PCB, where you can bend the PCB, and thickness of the PCB will be very, very thin in terms of so you can flex, you can bend the PCB so that your installation can be very easy, can be made easy, and some of the connectors are eliminated due to this, because of this technology, flexible PCB technologies. So you can see this connector portion, like instead of connector, you are using the flexible portion of the PCB. And this is the rigid portion of the PCB. This is also a rigid portion of the PCB, and these two PCBs are connected through the flexible PCB material. So the material is different from rigid to the flex PCBs. So the stack up of the multi-layer rigid flex combination PCB will be like this. The center portions of the PCBs will be considered as a rigid ports. So rigid area, means flex area. So that the bendability will be very efficient in the case of rigid flex PCBs. So with this, the basic of the PCB is getting over, and we will see quickly the design flow, how the PCB design flow happens in any EDA tools. So there are many ECAD tools. There is EDA tools, electronic design automation tools are available for designing the PCBs, and many top tier vendors are available. So for one such thing is Cadence, Mentor Graphics, Altium, and Zuken. So these are all the high-end players in the EDA market. This can be a PCB, or it can be a VLSI design, or IC design, chip design, package design, or whatever it may be. These people have this capability for this EDA purpose. And the Cadence has the Allegro and Arcade for the PCB design exclusively, and Mentor has the PAD Expedition Board Station. Now Altium has Altium Design, and Zuken has Visuala and CADStar Design Force, etc. So these are all the things. So there are open source tools also available, which also performs equally well, but there will be some limitations compared to these tools. So for this today's demo, I am going to choose a Design Spark. It is a open source tool which is from the European country, and for small project levels or research level projects, it can be definitely done using the Design Spark tool. So I personally feels satisfied for using this tool. So I'll be using the tool for this demo. And for any EDA tool, we'll be having this kind of correlation, right? Like we need to have the logic design and the physical design and analysis and verifications and another part of the design. So logic design will have definitely a schematic capture, that is circuit design and circuit capture, and variance and reuse, FPGA integration. So all these can happen in the case of logic design. And in the case of physical design, you will have the PCB design layout, PCB layout, and where you will place the component and you do the routing, which may be an interactive routing or the auto routing or manual routing, and preparing for the manufacturers, preparing files for the manufacturers. So there are for preparing files also, there are many standards, like universally accepted standards in Gerber format. The Gerber format is a text format where you will have only the size and shape of the trays or pads which is present in the layer. So you will not have the full intelligence of the PCB. It will have only the basic contents which is sufficient for manufacturers to produce a PCB. And the next is definitely a simulation side. So simulation is analog simulation, can be a mixed analog digital signal simulation, and HDL simulation, and signal integrity analysis in the case of high power integrity nowadays, and electromagnetic interference also it can be included, and the analysis and verification side. In the PCB side, the logical versus physical symbol is actually, so you can see the left side shows the actual component of an IC, and then nearby it is shown the logical representation of the IC. So you have to have clearly two views. You need to create two types of components for the same two types of symbols for the same component. Like it is a physical means actual, and logical components. So there will be a component editor, that is a library editor, which will have the facility to create the logical symbol as well as the physical symbol, which is also called a footprint model. Footprint is nothing but an actual size of the PCB. So in the case of ECAD libraries, so you will have to create the library initially, and from the library you are going to pick the component, whatever there will be a universal library, there is global library which is come by default while you install the PCB editor itself. Apart from that, if you want to create your own custom component, you have to create a library, and from the library you need to create a component based on your data sheet. And there are various processes involved in creating the library. First, you need to create a symbol library, that is like the logical representation. Again, next process is you are going to create a footprint library, that is a physical representation, actual product of the PCB, actual component size of the component which is going to be used in the PCB. And the third is, this is an optional thing. This is 3D model. It can be a step file or a SAS file or whatever it may be. So 3D model of a component which is going to be installed in the PCB has to be created. And we need to integrate these three types of symbols, that is physical, logical, and 3D model. You have to create one common reference designation for these three types of individual components. So we'll see how we'll create in the demo session. And there are another major things are involved, or in the case of engineering side, that is PCB engineering side, you will have to consider the floor planning, interfacing, speed considerations, power considerations, and the frequency considerations, and electrical constraints, signal integrity. So various things you have to consider. In the case of product, the same thing. So the EMI verification has to be done in the PCB level itself, and bus planning, high speed, and other related to the product consideration has to be done while designing the PCB itself. So this is a flow of the thing. So first we have to create a circuit, that is a logical representation, and we need to create an actual representation of the PCB, that is actual size of the component, with the size of the component, and making the connections, and you are making the actual board. So we'll see one by one a quick maybe like schematic means it's a logical representation of the circuit. So we saw you have to create a schematic library initially, and from the library you are going to load the schematic symbols in the schematic editor. So netlist concept, there's another concept is called netlist concept. That is the net in the sense, net is also referred as a signal, which is connection between two pins. You can say it is a connection between two pins. There are various netlist formats are available. So depending upon your EDA tools, the formats will be differed. So the net concept is nothing but a signal connection in the circuit. So you have to create the connection initially, and after that you have to come to the layer designing. And In the EDA tool, as you know, if you see some other tools, you might have heard grid concepts. So similarly, all EDA tools will have the grid components for easy layout. And for any component, before creating, you have to select the component, and you have to check the component producer, that is manufacturers, and from that you can see the part number, and you can collect the data sheet or catalog which is released by the component manufacturers. So this is the data sheet shown here. So with the actual data sheet, there are many electrical and other performance characteristics will be present in the data sheet. Also, there will be a physical size of the component dimension. Also, it will be mentioned. There may be a component which has the various multiple packages will be released for one component and one particular value. For example, resistors can be a 1 ohm resistor, 1 k ohm resistor can be leaded component, or it can be a leadless component. There's SMD component, surface mount device component. So based on your requirement, you have to select the component and you have to create the library. So as a summary, you will have two editors like this schematic editor and PCB editor in any EDA tool, and you will have a common library like component library. In the component library, you will have two libraries, additional libraries like schematic symbol, that is physical logical representation, and PCB symbol for physical representation, actual representation, that is called footprint. So another thing you can add on with this is 3D modeling, 3D diagram of a particular component. So all these three together will make a library, component library. And from this component library, you can insert or place the components in the schematic editor or the PCB editor. So this is the summary of the thing. So next, so you'll see this is symbol is we need to, as I said earlier, it is this is symbol. This is symbol is connected between the components and according to a circuit. So this is called schematic, and the connection between those components will be made through wires in the schematic editor. So there are various toolbars are available for making the connection and making the net name, that is signal name. So before starting the layout, we need to consider some of the main points, like what will be the maximum hole size in the PCB, what are the maximum trace width of the PCB, and what is the trace to trace distance and trace to trace clearance, and maximum board size. This is a very major factor, and this defines the number of layer. That is, if you keep on increasing the number of layers, the manufacturing cost will be very high. So we need to consider that also. So limitation concerning the board shape. Is there any shape restriction, or it can be a circle or a square, or we can have multiple combination of shapes. So we need to consider those things prior to designing the thing. So this is the typical design flow. While starting the PCB, you have to set the environmental options, design technology parameters, and we need to input the netlist. That is, netlist is the connections between the components as per the circuit diagram. So between the signals, so signal information you are going to input, and you are placing the components and making the routing and post processing. Some of the post processing has to be done for better performance. And finally, the Gerber or Gerber review or the Gerber release. That is, Gerber is a exported format of the PCB, which is for only manufacturing purpose. So this is a typical footprint creation process. First, we have so here we are going to create the two types of symbols, like one is logical and the physical, as actual representation, and we are combining these two with the common component library and using for the schematic editor and PCB editor. So after importing the netlist, you will have these rubber band lines. That is, between the components, you will have the connections. using those lines, those yellow lines are called rat's nest. This is actually a connections between two caps. And based on your need and requirement, you can decide the board size. There is board outline, you can say, and a few routed connections also here. I have shown here. That is in this area, and the green side there is actually a top side components, and the bottom sides are the red. Bottom side placed components. So we have to place certain connectors peripheral, which is very close to this proximity to the board outline, or the main processor like FPGA will be the center of the portion, or if based on the frequency, based on the signal, that is a mixed signal or the analog or digital signal, you can segregate the complete module based module in the PCB itself. Otherwise, there will be a integrity issues will be happening, or the other performance, PCB performance efficiency will be affected. So another layer of the internal layer may be a ground layer or a power layer, where you can pour the complete copper based on your voltage. That is 3.3 voltage. All the 3.3 voltage pins are grouped together, and similarly here the 1.8 voltage are grouped together, and inside the border you can pour the copper, and you can connect, make use of the connection. So this is called a plain layer. So the dark portion of the copper is called dark. That is dark color is you can consider as a copper side, and the lines which is shown the separation between these two voltages are can be considered as etched portion. That is copperless portion. And here the shown the typical 4-layer board, that is signal, ground, power, and signal. So signal refers to the top and bottom layer. So the distribution of the ground and power can be even. So the number of layer used in the PCB is also a even number. So it should not have the odd number of layers. So you can see this is a fine pitch component, and this pitch component cannot be routed with a high trace width. So for that purpose, we'll fan out the pads and the components that is captured in the component, and it has to be routed from this via. So this is a routed completed board on the top and bottom side. So as I said, analog and digital circuits has to be separated by the frequency range. So similarly, power circuits also will be separated from the analog and digital signals. So placement of the components has very essential part in the case of performance. Then we can go for in the case of PCB design. So we need to clearly mention the return path of the current. Otherwise there will be a signal integrity issues. So the return path, that is ground, it has to be returned through ground vias. In case of low frequency, the return path occurs to the least resistance path. So you can see the driver from the driver, the signal is passing to the receiver, and the return path can happen the next layer through the ground plane layer with the least resistance path. In case of high frequency, in terms of gigahertz, it will not follow the least resistance path. It will follow the least inductance path. So if the second layer, that is the next layer, the ground layer is a discontinuous one. That is, it is not a completely poured continuous plane. The return path will have will take the deviate from the actual low inductance path. So in that case, the displacement current will be high, and the performance in the receiver side will not happen as per we expect. And placing the signal traces. So there are other standards available in the APC. So based on your current carrying capacity, that is, for example, if it is a 0.3 amps, you have to use 0.01 each. So there are various simulation tools available to maintain the impedance level or the other parameters. So these simulations will optimize your needs and will give you can use those optimized results in the PCB. So similarly, you need to maintain certain distance between the traces, otherwise the crosstalk will happen if it is very close to the one. So this is a cleaned up silk screen shown here. This can be printed out and used for the assembling purpose. So this is just solder mask layer. And finally, we are going to export as a Gerber format. So this is the Gerber format output, which is very as in the Gerber format, we'll have only the XY information, that is location information and the size information. So with this, I'll close the presentation and I'm going to show the demo of the presentation. So if you have any doubts, 1 or 2 minutes, you can discuss on that. Shall I proceed for the demo?
Yes, ma'am.
Okay. So I just double click the designs part. So this is the designs. This name is design for that is it's an open source EDA tool for PCB design. So it will give the extensive features for doing the complete entire PCB design. So and this is the main first window. And initially we need to create a project like file new. So you can select the project menu. You can use a folder. You can give the project name. So the project extension will be date.prj. Then press OK. So you can see other project is created with the name of .prj file, and from here you have to create new schematic design. So as you say, as we saw already, there will be two editors. There is one is schematic editor and the second is the PCB editor. And these two editors has to be linked with the library part. So library, next as a next step, I will create a library. So as of now, one project, under the project, you will have the schematic design and the PCB design. So go back to the same folder. You can give the app name. Okay, then press OK. So you can see one more .sch file is, that is sch is actually schematic editor. So this file is created. So this is the window of the schematic editor. So if you double click or if you can see, you can close under the project, you can see the .sch is added, and if you double click this window, it will open here. So you can see the grid here. Then I am going to create a library for PCB design. So initially, so there are, you can see there are schematic symbol library and PCB symbol library as we saw, we need to create two types of symbols, like physical symbol, physical representation. I mean, logical representation initially, that is equivalent to schematic symbol, and the PCB symbol, that is footprint. And these two symbols has to be linked with these two has to be linked with the same component library. So for that, this tab is used. And if you want to have the 3D view of the component, for example, if you take um, so it is default library which is present in the design spark folder itself. So you can see. So this is 3D part of it. So similarly, so these 1, 2, 3, there is schematic symbol and PCB symbol and 3D view. So these three consist of a this consists for so you can say it's my schematic library name. So just say
You join it soon, very soon. Actually a small network issue. The resource persons will join say within 2 minutes.
So I'm extremely sorry for the internet issues. So due to some other, I think cable problem, I think so. I couldn't continue for the past 5 minutes. So I'm extremely sorry for this. I'll share my screen. So we discussed to create the library of in using the library manager. So the library manager can be obtained using this tool, and we have to create the schematic symbol, PCB symbol, as well as the 3D view. So 3D can be designed with the help of the mechanical tools like SolidWorks, like other AutoCAD or whatever it may be. So some of the manufacturers also will release the 3D component view. So you can just import from the thing. So these are all the tools available by default in the library, Design Spark library itself. And from here, you need to create the custom used schematic symbol, and there is a logical representation and PCB symbols for the actual PCB footprint. And you need to correlate these two this is optional. 3D view is optional, and definitely we need to correlate the PCB symbol as well as the schematic symbol as a component. So that is the thing we have to create. So initially we have to create a new library. So here I have created the SCH library, and for under the PCB symbol also you need to create a new library. So you can call it as a PCB library. So you can see the library name is PCB library, which has no files in it. So we need to create these. Similarly, SCH library will not. It's a new library which is created now, and component also we need to create a library. So similarly, you can see under the particular drive folder, and I have created a component library for the PCB design. So I leave this 3D view part as of now. And for the schematic symbol, let's start with the schematic symbol. Using this wizard button, you can choose any type of packages which is going to be used in your PCB design. So similarly, you can choose English or metric unit, and the precision level with the three decimal or 2 decimal, or you can that also optional for your understanding. And the second type is the second module you have to address is the type of your PCB package. Like some of the things that can be op amp or connector, or it can be a IC. So this is you can keep in mind that it is just a logical representation. That is, the tool just will understand the pins and the other concepts. So for as of now, I'll select this rectangle, and I'll create a diode or LED using this wizard. Then just press the button, and this you can play around, can change according to your design view. And this is a major portion we have to address correctly. And I think another, again, it has a problem. So hope my screen is visible. So we can give a name for like LED, and can finish with the help of the finish button. And so you can see there is physical representation, that is logical representation of a symbol is created here. And similarly, in case of PCB library, you can create using this wizard. Here, you just press as it is asked, and you can select a package if you what you want to have. Like if it is a DIP package, you can select like this model. And if it is chip capacitor or chip kind of things, or VGA kind of things, so there are various packages are available. You can choose what component you want to design. So for example, I choose this DIP package, and you can press next, and total pins I want to have is 2. That is the same LED component. That is, I'm creating a schematic symbol, PCB symbol, and component library. So these measurements values you can give as per your data sheet. So for example, this 2.54, there is 1 mm, E is 1 mm, that is E is distance between this pin pitch. So here there is a two pin component, so you can ignore this value. And pad width and everything you can present, you can change here according to your data sheet, which is released by the component manufacturers. It will be normally in the PDF format. You can see, you can give the name. You can give same name as LED. So you can see the LED component is generated, and the important point is we have to correlate this PCB schematic symbol and the PCB symbol. So for that, you need the component library for correlating this. So first select the wizard type, and can just press next, and give the name as a LED. So 3 times you have to create. And symbol is package type is through hole. Can select through hole, and LED you can reference can be a L. So if you place a multiple component, it will have L1, L2, L3, L4, etc. So number of components pins are 2, number of gates is 1. So press next. So here you have to select the proper library. So I select the Kongunadu library, that is LED, and then press next, and again I press Kongunadu library for the PCB. So you can see the flow from the left side. You can see the flow here. We have to select the schematic symbol first, then PCB symbol first, and then next subsequently, and other assigning pins in the third flow. So these 3 are major area to be designed done during the component creation. So from the PCB library, I selected the again LED. So here we are mentioning the schematic pin numbers should be equal to the PCB symbol pin numbers. For that, you have to assign 1 to 1. So this means that pin number 1 of schematic library will be equivalent to the pin number 2 of schematic library. Pin number 1 of schematic library. So 1 and 1 pins are same. And that is why, that is what we are instructing the tool to do. So next, just finish. So you can see the LED component is created. From this tab, you see only the logical symbol. Here you can see only the physical symbol. In the component tab, you can see both the symbols are correlated. So this is what we want. So similarly, whatever the components in your circuit has, you have to create each and everything. You have to add into this component. Some of the components can be taken from the common library like Design Spark. It is a default library which is installed inside the in the installation files. So we can select out of this also. So I hope the component creation is clear. And what the next step is we have to create the schematic symbol. So for this, I am taking the simple circuit like schema trigger, for which this 555 timer and 2 capacitors and 2 resistors and 1 power supply and 1 ground is used. So I'll try to go and create the schematic trigger symbol. I mean schematic trigger circuit. So for this, the library I have already created for 555, C2 and R2, etc. So I'm going to insert a component from already created library. So I can use add component. This window allows you to add the component inside the schematic symbol. So I have created the demo components for the demo. So just double click or press add to this. So you can just click, it will add a component. So if you add another component, it will come as a U2. And I have to add 2 more components like two capacitors and 2 resistors. So just press add. So you can see I am pressing again on 1 more capacitor. So 2 capacitors are added, C1, C2. And similarly add component for resistor. So R1, R2 are added. And I am going to add plus volt. It can be a 5 volt, or it can be, you can define the voltage level what you want, and ground. So these three, this is left side shows the circuit diagram already, which you have simulated for the output and input values. And this is a circuit schematic window which has the similar representation. There is physical logical representation of a circuit which you have. So I just rotate this R2 by rotate. Sorry, it should be 90-degree rotation. So I just move here. The simple click is enough for modification or any thing. So just rotate again 90 degrees. So I'm placing it here. And this is a capacitor. One capacitor is, we can give it as it is, and the other capacitor can be. So you can see you can rotate also. You can move the ground to near to the spin. So just pressing this button, you can add the connections, or you can use this add schematic connection. Just double click is enough for making the good connection. So just moving this will interactively will help to make connections. So I think the circuit is completed, or you can simulate this circuit, and you can add text. You can add the text name. I mean circuit name. You can give the actual name, and you can use this size information, whatever it can be legible or so like this it will appear. So you can change the font size or everything, and you can add the title of this uh, uh, job, and you can add the designer name or what, or in any other instructions, special instructions, whatever it can be, you can add, and you can save the file as .sch. So this is the .sch file, that is schematic file. From this schematic editor, you have to transfer this connection information. So this is called net information. That is connectivity information. That is called net information. So that net information has to be translated from the schematic editor to the layout editor. For that, you have to translate to PCB. So this will give some of the set of instructions which has to be followed as per this instructions given here. So next, so I am going to use the unit and precision as 3 decimal. Next, so it can be a 2-layer board, and the or whatever layers you want to have, single layer or it's also is possible. So anything you can choose according to your thing. And next, it will ask for the board size information. So as of now, I just leave the values as it is. So if you have any specific board size information, if it or it is a circle, you can select whatever you want. And it is asking the component where the component should be placed. So I am mentioning arrange the components outside the board. So based on my need, I will arrange the components inside the board. And it is asking for the PCB design name. So demo PCB I can do. By just pressing the finish, it will give the report. So the power and ground has to be defined as according to based on the plane. So for the power and ground, we don't have the components, so we'll be connecting through the power plane. So that is what it is mentioning. So you can see all the resistors and other components are placed here. So you can just pick and drop here. It will go to this. I mean, it can be placed according to this thing. So this rubber band line shows the connection between these two components. So you can see the connections are inverted, like it is crossed. So if you to make the perfect connections, you can rotate the component 180 degrees. So you can see here. So the making the connections will be easier for this. Here also, if you want to have the rotation, you can have the rotation and can move it here. So that you can make the connections easily. And here, so we can place here also it is crossed. So if it is rotated, you can route the trace easily. Let's see here. So now we're using this rubber band line. Now using these rubber band lines, we can make the connections. So prior making the connections, you have to set some of the environmental variable like design technology site, the path style, the text style, and the line style. So you can under the line style, so you can so default width is 0.127. There is 0.127 mm. So if you want to change the trace width according to your current carrying capacity, you can set here. I will leave it as it is for this demo. And you can make the layers settings on layer types, net connections, power and ground net connections, net class. You can group the net, some of the nets, and you can class it as a separate class, and you can apply for some special conditions to them. And spacing details, trace to trace I set as 0.254. By default it is 0.254. There is 1 mm, and you can make you can change the spacing details using this tab. And for so the setting variables are ready, and from here I can choose. I have to take the connections from one component to the another component. For this you can use add unrouted connections, or I mean add tracks you can use. So otherwise you can just double click on the rubber band line, and it will show the connection details. So here you can see all the traces are routed, and the 135 degrees, the acute angles are not engaged. So this is how we make connections. So similarly, you can have the complex designs also in this kind of thing, and you can save the design, and some of the reports can be taken out of this thing. Before that, you have to run the design rule check. So we have already initially we have set the rules, and we are checking whether the rules are met or not. So I just check for trace, that is spacing between traces. Already we have given 0.254 mm, which should be there for spacing between traces. So I am just checking the report. So it says the no error is found. If it is a less than 0.254 mm, it will indicate as a error with the location information. And so similarly, under the design rules, you can check all this spacing information. There is space, shapes to shapes, text to text, board outline to copper, and component to component, and the net completion report. So if you check the net completion, whether all the nets are completed completed for the routing or not. So if it is not completed, you can see I'm deleting on net purposefully for checking the net report. So design rule check, net completion report, I'm checking it. So you can see one error is found, and it is connected on the location information, and the error can be captured. So it is not connect. NC means not connect. So similarly, all the reports has to be cleared with, and get the no violation report, and after that you will be having the what to say, we have to export the Gerber files to the manufacturers. So for that you can use the output manufacturers. Before that you can take the reports for your reference. So under the report sections you can have bill of material, like what are all the components you are used in this design, and dangling trace report, that is open trace report, component height report, design rule check report, netlist report, that is connectivity report, layers report, net completion report, or the other necessity reports. It can be in the form of CSV files or position files or whatever it may be. It will give the reports according to your needs. So for example, I am taking the bill of material reports. It's a CSV file, it is generated. So in this design, I have used these 5 components with the name and designation. Everything is this is a reference number which is in the PCB. So all the detailed bill of material report is generated out of within a second. And after completing all the checks and reports, you can export as a DXF or the manufacturer's plot. So as I said, the Gerber format is the main common general universal format for giving the data, PCB data, to the manufacturers. So I am just taking the top, since this is a 2-layer, I can take the copper bottom copper, top copper and bottom copper. And if you want, you can take the silk or whatever, top silk screen, bottom silk screen. So whatever data you require, you can run, you can generate the report, and where the project folder is created, you will get the files over there. So this is the file format. This is a report, log file report of the plots generated. Okay, so apart from that, there are various tools are available. You can explore. That is, some of the tools are design calculators. Like you can calculate the trace with impedance to match the thing, and track impedance and VR resistance, how much resistance the VR carries, and heat sink information. So like conversion. So various tools, design calculators are available. You can make use of this calculator while creating the design PCB layout. And a normal measurement you can take between the pairs, or place the components, or you can between the board outline, and so you can just press the, you can select the measure, and you can select the two entities you want to measure. It will give the complete information about the distance and in terms location and in terms of other values. So similarly, auto routing is also possible. So in this job we have done the manual routing. So auto routing all nets are also possible using this tool. And you can update the component, you can edit the component here, and you can update the component in this editor itself. So in the library you might have done some mistakes, or the revision may be revision of the component can happen during the PCB design life cycle. So that can be incorporated in the designs during the design itself. So you can edit the component, and you can save back to the component to the library as well as the schematic editor. So you can do whatever the thing you want to do. So this shows unrouted nets. Unroute all nets, it will unroute all the nets. So you don't need to delete individual nets. So you want to take the complete placement. So first you need to do the unroute all the nets, and you can do the trace. So now we'll do the auto routing. See, the auto routing the traces of the auto routing had happened with a 90-degree trace flow. So this is the drawback which we see for the signal integrity level. So since it is a simple circuit, it doesn't matter. But if it is a high complex circuits like mobile circuits, you have to have the eliminated via. So see, via is drawn here. It automatically places the via, so it will increases the loop inductance. So it will have to eliminate vias by using the manual routing. So for some cases we can use the auto routing. So if you want to see the board in the 3D view, so this is a 3D view of the component. I mean PCB, which is so this is a top layer. You can see all the text are placed. You can rotate the text. You can play around with all these variables. Like you can rotate, or you can move the text or move the component. So this is the bottom side view of the component. So the green color, and this shows the board material. So like some various other features are available. You can highlight the net, and you can control the colors of your parameters. I mean your entities placed inside the board using this color boxes. So in the project window, you can see the two names are created. Already we saw this schematic file already. So after creating the PCB file, also it creates the .pcb file. So this is a complete project of a PCB. And for similarly for the schematic editor also, you have all the tools. Some of the tools may not be there in the schematic editor, but will be there for the PCB editor, which is very appropriate to this particular tool. And some of the menus are common for both the things. So you can add shapes. Here also you can take the reports. You can print the board. I mean, if you print the schematic like PDF or Windows. If you want to share the schematic to your manufacturers or your colleagues, you can do the print in the form of PDF. And you can do the settings here also, and you can trace lines settings and connection settings, nets. You can group the net classes, everything. So the same information can be translated in this editor with the help of the internal database. So here also you can see, you can add text or whatever related to things. You can do this. I hope you got some idea about the PCB design and its flow. So with this, I would like to stop my demo. So if you have any doubts, I am ready to clarify your doubts.
Participants, any doubt, any queries, you can unmute yourself to ask to our resource person.
I'm extremely sorry for the inconvenience happened during the presentation of this, for the internet connectivity issue.
No problem, ma'am.
This Design Spark is an open source tool you can install in your laptop or machines without any license thing. You can use for this is a very powerful uh, tool. You can use do the complete PCB design flow with this tool. So I can see this is equivalent to the competitors, I mean high end tools for simple projects or your final year students projects. You can recommend these tools. So I can guide them if you want in terms of designing activity or other thing also. Hope this session is clear for everyone.
Have you completed the session, ma'am?
Yes, sir. I am done with my side. If you have any doubts, I'll clarify, sir.
Okay, ma'am. Participants, if you have any queries, you can please put it in the chat box or just unmute yourself and ask the queries. No queries are being asked, ma'am. Shall we conclude the session, ma'am?
Yes, sir.
Kind words are short. Hope that her echoes are truly endless for us by this wonderful session. In this way, I'd like to thank our today's resource person, Mrs. Uma Maheshwari, on the topic PCB design demo in EDA tools. On behalf of Ponganadu College of Engineering and Technology, Department of Engineering, thank you so much, ma'am.
Thank you, sir. Thank you for inviting me for this wonderful function. And thank you so much, sir.
I'd like to thank all the participants who helped us to complete the session 2 of this day. Thank you all. Now we will provide the feedback link. Please wait. The chat box, please fill it out.